The current concept for the application of computer-aided engineering and finite element analysis in product and process design is to compute the simulation results to judge the feasibility of the method used to overcome an obstacle, a go, no-go validation of the design. The obstacle in this case could include formability, manufacturing feasibility, assembly, crashworthiness, vibration, aerodynamics, or other performance attributes. To overcome the obstacle may require the design of tools, new product features, processes, or other attributes whose performance can be measured using the CAE tool. A bridge, in this case, is used to illustrate this method of crossing the performance gap. In conventional applications, the generation of an acceptable result is a proof of the existence of a feasible solution, and is therefore interpreted as a justification of the design. The objective has been reached. However, with this attitude, it is often concluded that the first passing idea is the best, as if when we are searching for a lost item, we do always seem to find it in the last place we look. After all, once we found our lost item, there was no value in searching out other locations. But the solution to the problem that we seek is not a lost item to which there is only one solution, and to assume so is a mistake. Instead, we need to consider that possibly alternative solutions exist, and that those solutions are worthy of evaluation. This obstacle could have been overcome with a more complex solution, and indeed the designer may have considered this possibility. In fact, many designers will have applied their expertise and experience to eliminate from consideration this concept. Perhaps they had assessed that the alternative was too costly, too time-consuming, or even politically difficult to support. Still, other corrective actions could be shown as feasible as well. However, the good designer may have recognized that the risk of attempting such a solution was itself very risky, and that any benefits of this aggressive solution was outweighed by the chance that the solution might not achieve the objective. Considering only one potential solution at a time, any one of these solutions does appear to be valid. The first proposal found often ends the search, and that becomes the result. In the eyes of the analyst, the most immediate result is the best result, as the passing result signifies the completion of their task. The consideration of alternative concepts are often thought to be outside of their realm of influence. The simulation analysts and the designers they support are measured on the fact that the solution has been proven. However, if we consider the other potential metrics of cost, time, as well as the relative risk involved in applying a solution, then we see that the first passing solution is not automatically the best solution. Extending this concept, we must not overlook that the existence of the obstacle that was encountered was a direct result of the decisions made earlier in the design process. If we roll back the clock and consider perhaps an entirely different product or process design, it is entirely possible that an alternative exists. Taking a totally new course of action might result in a different associated cost, and certainly there would be an infinite number of combinations that would allow us to achieve our objective. Therefore, the use of CAE tools to validate is not the only necessary tool in our toolbox. It becomes clear that we need to evaluate these solutions on criteria more broad in scope than only those performance attributes from CAE or FEA tools, but also on cost and timeliness of a solution. So because the achievement of the objective is not the final result or the final end game, we must have a comprehensive approach that allows us to evaluate not just the attainment of the objective or function, but also that we attain a certain level of quality, desirable cost, and that this result is available in a reasonable time. A comprehensive approach for computer-aided engineering and feasibility analysis represents a significant departure from the perceived roles that an individual might play in most design and manufacturing organizations. A typical linear progression of analysis optimizes a design for pure functionality. Only later do we consider the cost of achieving that function, then the manufacturing quality attainable, and finally, whether or not that impacts our final time to fulfillment. It is inherent in such a system that there will be compromises in the attainment of criteria in each function. Compromises, suboptimal conditions, and even outright discarding of criteria are considered, which were considered critical in prior evaluations. If instead we could define the additional metrics beyond the scope of typical computer-aided engineering, we will indeed be more successful in seeing that the designs that we validate using CAE have a greater likelihood of fulfillment. When evaluated in this comprehensive manner, we could observe if one of the safe designs is indeed superior to another. Measuring for quality, function, cost, and time of fulfillment, we could observe the quality of one design, and then, when compared to another design, see if that was indeed superior in its ability to deliver on those desired criteria.